friends, welcome back to another session on operating systems. We are into our second module, process management, in which we have been looking at the various scheduling algorithms where we have multiple processes or threads available which are to be attended by the CPU, and if the number of CPUs are less than the number of processes or the threads, then some way the processes have to be scheduled. So in the previous sessions we have seen when we have a single processor how that can be done. Now let's get into a system where we have multiple processors. That's what we have been achieving because of improvement in the VLSI technology, and also the chip size is reducing, and because of which on the same processor we have multiple cores possible, and even we are not happy with a single processor at any given time, so we would like to work with more than one processor in parallel so that the overall activity can be speed up. So various reasons are there. So for all that, what we do have today is multiple processes are available, and we have multiple processes are to be scheduled over these multiple processors. So let's see what this scheduling is all about. So multiprocessor scheduling is how the operating system schedules the processes or the threads to run on more than one processor or the CPU core. So it may be multiple cores of CPU in one chip, or there can be multiple chips, each may be having a single CPU core or multi-core. So there are many versions available. So when we have such a situation, that means when we have more than one processor available for working with the jobs, then how to allow these jobs to be run by the processors is what we are looking at. The major challenges we would like to look at while working with multiple processor scheduling is how to distribute these processes or the threads across all the available CPUs. So when a new process comes up, then to which CPU or to which core we should attach that process or the thread. So that is our first challenge we do have. So how to distribute all the current processes on the ready queue to various processors available, that is our challenge. And the other challenge is yes, one is distributing, and while distributing we should ensure that the load is also balanced. So we are not sure at the time of allocating a CPU to any process that how long the process is going to run and all that. It all dynamic in nature. There is nothing predefined that this process is going to run for this unit of time and all that. So we don't have any such information in advance, and because of that it becomes very difficult to ensure that all the CPUs get a equal share of jobs, so that all CPUs are either not overloaded or not waiting for any job to come up. So they should have some reasonable number of jobs at any given time. So to ensure this load balancing is another challenge we do face when we are working with a multiple processor environment. And we need to ensure that the contention and the overhead is to be minimized, because when we are working with multiple processors and then we are scheduling it, and say that if we are working say on the round robin type of scheduling algorithm, then at any given time the job was allotted to one CPU, and after its term is over, then it is sent back to the ready queue, and next time when it gets a chance, what is the guarantee that it gets the same CPU next time? so it may get some other CPU. Then the problem with this is the processor which was having already working with a particular job was knowing all the details like the data, the program counter and all details were there with that. That is a process control block details, everything was available with that processor. Now next time if it is allotted to some other processor, then this whole thing has to be reloaded there, and that may take extra time and all that, so that will be overhead, and that has to be made minimum. Then the another issue is about how to handle the shared resources and the private resources. So each process has its own private resource like memory. Then when a process opens a file, then that file has to be available only to that process till that process completes its job. A file should not be allowed to use by some other, otherwise there will be overwriting of the data, and that may create inconsistency in the data. So not to have such problems, we should have a private access to the resources. And when we have such situations, and when these are being addressed by multiple processors, we do face many challenges of having shared resources and all that. If a whole thing is under one chip, yes, we can share the cache memory and all that, but if they are on the different chips, then we have to refer to the primary memory for sharing and all such issues. So that is another problem we do face. Then coming to the types of the multiprocessor system. Coming to the types of the multiprocessor system, we have two main types, that is symmetric multiprocessing and asymmetric multiprocessing. If we have a different physical processors in different chips, or it may be a multi-core processor on the same chip. So if we are talking about different chip processors, then symmetric multiprocessing is one where all processors are having equal rights and the same operating system. They share the memory and they share the scheduling type and all that. But in case of asymmetric multiprocessing system, there will be one master processor, and that controls all other processors, and this is simple in implementation, but it is less flexible. And the third one is a multi-core processor, where multiple cores are there on the same chip, and they share the cache memory and the memory buses which are there inside the processor. And these memory buses inside the processor are working at a highest speed. Therefore, the operations performed, communication among these cores are done at the highest speed, and they share the cache memory, which is again working at the processor speed. So the activities do happen at a highest speed possible. Now the various approaches for scheduling. One is the load scheduling, where we say that it's a global queue we have. Here all CPUs are pull the task from a common queue. So there is one common queue where when any process or a thread comes up, it is put on the queue, and whichever CPU becomes free, it pulls the next available process from the queue. So it is simple, but definitely can lead to cache misses and synchronization overheads, because as we discussed in the few minutes back, that if we are talking about a round robin like thing, then the task once was being performed by one CPU, and next time it may be performed by some other CPU. Then the data sharing from one CPU to other CPU will take an extra time, so it's going to be an overhead. Synchronization will become a problem. And definitely the one processor is working, then it has its own cache memory, then the data required or the process code required for the next few steps are dumped onto the cache memory of that particular processor. But the next time if it is scheduled to another CPU, then we need to make sure that all the things are rewritten properly onto the another processor's cache memory, and proper synchronization has to be taken care. So it's going to be a little costly affair when we work with a global queue. Otherwise, what we approach is processor affinity. That is, you just one process is connect to one CPU. No matter how many other CPUs are available, you just pin one processor to one CPU. So in that, what happens, whenever that CPU is free, that process will be running. Now the benefit is this cache performance will increase, and there won't be any migration from one processor to another processor and all that. So that can be saved. But only a problem is load imbalance. That means this particular process is waiting for a particular CPU to become free. Though all other CPUs are free, this process cannot run because it is attached to one particular CPU. Therefore, as long as that CPU is available, this process cannot continue further. So there will be a problem in the load imbalance, because some CPUs, though in the beginning the load sharing is done properly, but we are not sure how long each process could run. Therefore, some process may exit early, some process may run for a longer period, and if some process attached to a particular CPU run early and that CPU is now idle but cannot work because it doesn't have any CPU attached, any process attached to that CPU, though many processes are waiting for their turn, but they are attached to some other CPU, so cannot continue. So this creates an imbalance in the load. Another type is the load balancing type. So it's an extension of the previous one. Here, when we know that one particular CPU is overloaded and other CPUs are idle waiting and not having any other process to work, then this overloaded CPU can be relieved by shifting some of its work to another CPU, so which we can call work stealing. So through this, what happens is the load gets balanced. So because of this, all CPUs regularly will be getting almost equal amount of work, and that ensures better CPU utilization, and this is commonly used in the modern systems like Linux and Windows. Then we have another type of scheduling possible, which we call gang scheduling. Here the related threads and processes together are scheduled. So all the processes which are related together are scheduled together. So that's gang processing, and because of they have some similarity, they work together, they can work in parallel, so the synchronization overhead can be reduced through this gang scheduling. It is often used in the clusters. So overall, if you just look at the comparison among all these, so the load sharing, the first one, which is going to use a global queue for all the CPUs, the positive side is it is simple, it is fair. The negative side is lot of overhead and poor cache locality. Then second one, we said that pinning a particular processor to a particular CPU, that is processor affinity. Here we pin threads to a specific CPU will provide good performance, but there is a risk of load imbalance. The third one is to overcome this risk of load imbalance, we thought of having load balancing scheduling where the overloaded CPUs are relieved by moving the tasks from them to idle tasks, idle CPUs. So this keeps all the CPUs almost busy all the time, but requires a very smart algorithm to identify which CPU is overloaded, which CPU is idle and all that, and how to manage the whole thing. A smart algorithm is required. And finally we have gang scheduling. Here the related threads are run together, and it is ideal for parallel programs and definitely needs a lot of coordination. Otherwise it's going to create a large problems. So that's something about multi-process scheduling, some overview about that. And that's it for now. Thank you.